Hi, so over the summer I built this thing. It's a deck and pergola and a little summer house, and I did it because, well, we're having a glorious summer. I wanted the kids round for a couple of Barbies, and that's exactly what we've done. Because now we're coming into the tail end of summer. We're starting August, and of course we're going to come into autumn, and dusk is going to draw in. At the moment it gets dark about 9 o'clock. In a couple of months it's going to get dark about 7 or 8, and those evenings are still going to be enjoyable but sort of lost. So I decided to put some festoon lights up, and they look awesome in the dusk, and it makes a really sort of cozy kind of space where I'd like to extend that time, and so I put lights up. Now, of course, when putting electricity into something like the back of your garden, you have a number of choices. I mean, I could have just run a wire to the house mains and put it through some IP rated gear and we'd be on a winner. But I decided to give it its own power supply with these things. Yes, I'm going to put up a bit of solar. Now, I bought 4 of these 120 watt panels. I think they're 670 by 960 by 35 mil deep, 120 watts monocrystalline panels. And all solar basically it's the same sort of stuff. It doesn't matter much whether it's a little garden light that you're putting in that charges itself, a set of solar panels like this, or even a bigger installation. They all follow the same principles. So I thought what might be interesting is a video where I put this solar in and we talk about that stuff as I'm installing the solar to be able to run my lights. And I thought about putting the Halot out here. The Halot by Pyocrete is of course a resin-based printer, and they do the best with resin to make sure that it's not stinky. But it still is, and it's one of those things that puts me off using it in the house. So I've got a work shed right there, and I thought I'd put the printer in there as well as some lights. So what kind of things do I have to think about? Of course, the first thing is where to stick it. Now, I've got that shed right there, which is where the Halot's going to go. And that shed actually more or less faces south, which for me is that direction. Now, I'm in more or less the same latitude as London, which means I need to angle those solar panels at the best at 35 degrees facing south. So as the sun transits, it gets the most sun. Now, it's between 30 and 40 around where I am, but I'm aiming for 35. So my plan is to stick them on that roof, angled at 35 degrees, facing straight out that way, which is south. Now, of course, that's quite a convenient position, and you can get it as near as that. Every time you move off of that, you're going to lose a little power, but the nearer you can get to that, the better it is. But it's more of a guide and not a straitjacket. So, first thing is stick them on the roof. The next thing, of course, is why on earth did I buy 4? I mean, 4 at 120 is roughly half a kilowatt. That's the generation power at the best. Incidentally, these are reported to be about 20% efficient, which is pretty cool. But it's supposed to be half a kilowatt. Now, I know it's not going to do that, so I've kind of taken 20% off, and we're looking at somewhere around about 400, 350 watts generation over an 8-hour period, something like that. But I've picked this number for a specific reason. And the reason is these lights I've got up here, well, they're a 12-watt draw. The Halot is a 60-watt draw, so I'm going to be able to light these lights. If this gave its full output and I put it all in the battery, I'd be able to light these lights 133 days non-stop, which is crackers when you think about it. But it does mean that I'll always be able to turn the lights on, even if I use the Halot. Well, it'll give me something like 32 hours of use, something like that. So, plenty in order to be able to use the lights and the Halot and a couple of little ancillaries. Now, you might be thinking to yourself, well, that doesn't sound right. I mean, you know, it's 60 watts and they're 480 watts in total. That's more like 8 hours, not like 32. But you're forgetting that I'm going to put it into batteries. And of course, the question is, how many batteries do you use? How much batteries? Well, at 480 watts or 8 hours of charge, I have a potential of something like 4 kilowatts or so. So I didn't use anything. They were outputting at their full output it would generate in an 8-hour period something in the region of 4 kilowatts. So that's the power I have, because of course it continues to generate even though I'm using it. And where is it in that slope? Well, that gets very confusing, and so you just think, how many hours on average of sunshine will you get? What's the output of your panels? And then what's a reasonable amount of battery storage that can store that output? It turns out about 4 kilowatts of battery is going to be plenty to take the output for those panels. So I've got, by rules of thumb, a rough size of a system that I want to be able to do the job I want at the bottom of my garden, to prevent me from having to run a wire. And of course it gives me experience in putting up a larger, more complicated solar system than a garden light, and then can lead to maybe a bigger system in the house, having gained that experience in what is relatively an inexpensive way. Because I paid £300 for all those solar panels, plus the solar charge controller. And here is the solar controller. Now the solar controller is just a bunch of electronic components that go between the solar panels and the batteries. It's just like plugging your car battery into the wall, only it has a little bit more control, and it makes sure the voltage from these things is converted into the voltage your battery needs, is sent to the battery, and also makes sure that it doesn't overcharge the battery. But it's really simple. It's solar panel, controller, battery. And of course a whole bunch of cables, but they usually come with the panels or the controller anyway. So with those 3 parts, we're actually more or less ready to install our system. So let's have a quick think about what we actually did. The first thing we did is what's called an energy audit. Have a think about how much you're going to actually need. So we've got 12 watts here, a couple of lights in there, say another 8 watts because they're 2 at 4 watts, and then 60 watts for the printer. We're looking around about 80 watts that I'm going to need. So bump it up for other incidentals and we'll call it 200 watts. Now if I use 200 watts for an hour, that's 200 watt hours. So how long do I want to do this? Well, more or less a day, I guess. So I'm going to need it to run for about 24 hours. And it turns out that 2 kilowatts would be 10 hours. So 4 kilowatts is going to give me about 20 hours, which is more or less a day that I'm going to use it. So in a day, if I were using everything fully, these panels could charge my batteries, and my batteries could fulfill my energy needs for a day. Now, all of that is fine and a bit rough and ready for fairy lights at the bottom of the garden. Now, if you want to do something a bit more complex, then your energy audit needs to be a bit more complex. The kind of degree that you need to give it for latitude, so I'm allowing, quite a lot really, 4 hours difference for a whole day, but it's fine for me. But the degree of latitude you want to give it is something you must estimate. When you estimate that, that'll give you the size of the system you actually want. Once you've got the size of the system that you want, well, you can start buying your panels, you can start buying your batteries, and you can choose your solar controller to go in between them. Of course, the power from the battery needs an inverter to be able to make it usable in a house, which is a 4th component you need. We'll talk about that a little bit later. And of course, there are other choices that you need to make, but those are the basic choices to get you up and running that you need to make about these things. Now, some of the choices you're going to make once you've done that is what kind of panels do you use? I mean, these are monocrystalline, single-facing panels. They're probably the cheapest and easiest to get hold of. You can get bifacial panels. That's where they have solar panels on either side. Now, I'm going to stick these at a 35-degree angle, so bifacial is no use at all to me. But it has been discovered that if you just hang them straight up and down, over time, they're actually more efficient than lying them flat. And it's a simple reason. I just drove down my road and lots of people have got solar panels up there and more than half of them are just covered in bird poop. Who's going to get on the roof and wash a solar panel? Nobody. And so if you hang them flat, of course, they don't get covered in quite as much dirt. And so over time, they're more efficient than if you hang them straight up and down than if you lay them at that 35-degree angle. Or so the research tells us. Me, I'm going to stick with the 35-degree angle, but It's a choice that I've made, and it's a choice that I've made when deciding on the particular panel that I'm going to use. Because this thing, it's a whole bone of contention. The solar charge controller, there are a couple of major types. There's something called pulse width modulation and something called MPPT. Now, it's without a doubt that MPPT is far more efficient than PWM, pulse width modulation. It's more efficient to the tune, I think it's about 30% more efficient or something like that. Unfortunately, of course, they're also more expensive. They're something like 50 to 70% more expensive. And so it's a choice that you need to make. Do you spend more on it, getting a more efficient one, or do you spend less on it, getting a less efficient one and just buy an extra panel? It's that kind of choice. And there are always choices. And of course, you'll find a legion of people telling you that one way is better and the other way is better. At the end of the day, it's a choice you want to make, and it always comes to efficiency versus cost. There's another choice, and that's redundancy. I'm a huge fan of redundancy. I'm a fan of what's called the RAID network in computing. The RAID stands for Redundant Array of Inexpensive Disks. When they first started producing large capacity computer disks, they were really expensive. They could carry terabytes, and if they broke, you lost everything. So what people actually did was buy cheaper disks of something like 250 gigabytes and run 8 of them at the same time. It was actually cheaper to do it that way, and if something broke, it didn't take the whole system down. And I'm quite a fan of that, particularly when it comes to things like solar. But that's a choice that I'm making. If you want one big system that you don't have to look after, then great, go for that. If you want it broken up into smaller sections so you have redundancy, but it'll take you a little bit more setting up, then great, go for that. It's whichever suits you. Me, I'm a fan of redundancy, and so I'm going to use what's called a redundant system. A redundant system is going to be these panels grouped into charge controllers, but with a smaller charge controller per panel rather than one big charge controller that covers all of the panels. As it happens, this is beginning to be the way that solar panels are going. New solar panels these days carry with them what's called a microinverter. You'll see them on the back. It makes them cheaper and easier to link up, and if a panel goes, your whole system doesn't go. They're putting the microinverters in the loft, and so repair of it is much, much easier than having one big inverter sitting in your garage. So redundancy is also coming through in solar. I'm a fan of it. If you're not a fan of it, don't do it. Go for one big thing that will actually do everything. Work out your panel size, work out your battery size, and then buy the solar controller that suits the size of your system. Me, I'm going to break it down into redundant parts and get the solar controllers that will match those redundant parts. It also means that if I've got it wrong and I need a bigger system, then it's much easier for me to add on to my system, which is another reason microinverters are coming in, than trying to resize the system and get a new charge controller for it, which will be an absolute pain in the neck. So I'm going for a redundant system because I'm going for a redundant system. It appeals to me. It fits what I think. If it doesn't appeal to you, don't do it. If you want to choose between PWM and MPPT, have a look at the difference. If you prefer MPPT because of whatever reason, sure, go for it. If you prefer PWM for whatever reason, sure, go for it. What really matters is it's solar panel, controller, battery. Now, batteries are going to be another huge bone of contention about what kind of battery is best. Turns out what kind of battery is best is one that suits you. Now, I'm going to use lead acid, and that means that this controller can cope with lead acid, and that may seem like a throwback. But as it happens, I have 4 lead acid batteries sitting in the garage that are up to 4 kilowatt hours, and so my batteries aren't going to cost me extra because I've already got them. Probably if I didn't have them, I would go for lithium, but I'm going for lead because I've already got lead, and I don't really see the harm in that or the worry about that for the next couple of years. Later on, if I need to change it or I want to change it to lithium, well, I can do, as long as my controller can cope with it, or given that I've got a redundant system, I could also change the controller quite easily as well. Now, I don't think I was 100% clear there. If I've got a system at 200 watts and I run it for an hour, and that's 200 watt hours. If I run it for 2 hours, it's 400 watt hours, 2 times 2. If I run it for 5 hours, that's a kilowatt. 10 hours, it's 2 kilowatts. 20 hours, that's 4 kilowatts. So that amount of power is what I need to store. Equally, if I have a storage of 4 kilowatts and I withdraw 200 watts an hour, it will last for 20 hours. So the way you work from watts to watt hours is watts times time. Now, you're going to be faced with decisions all of the time, and at the end of the day, actually, truth be told, your decision is going to be somewhere between what you want and what you can afford. Now, I've gone for these things. These things are, in fact, PWM, pulse width modulation. They're not MPPT, which is multi-power point tracking. The reason I've chosen that is because this particular one will handle lead acid and it will handle lithium, which is what I want. And it also actually would handle nickel iron, which I'm considering when it comes to building your own batteries. So it's got a wide range of batteries it can cope with, and it's relatively inexpensive, which is what I wanted it for. So that's my choice for those reasons. You have different reasons, and so make a different choice. But the important thing is to make a choice. Now, very often, beside that, what choice you make barely matters. Go left, go right. It only really matters that you make a choice and go that way. That's how you achieve things. By wandering between the two choices, actually you'll just make a mess. And are you making the best choice? Well, given the information you've got, probably. A lot of this stuff, of course, I don't know. I looked up what the angle was for placing solar panels in my location. If you're a bit worried about stuff, well, you can just look it up. When it came to the power draw of things, I looked it up on the internet and it gave me the power draw. So use the internet as a valuable resource of information. Make a choice that suits your budget and what you actually want to do with it. Accept any constraints on that choice, because you'll never get perfect, and then move ahead with your project. Here we're going to actually do the installation. Now, don't get too tied up on specifics. All of this stuff is really an example of how you go from A to B. Your A and your B may be very different, but how you go there tends to be the same. So, of course, obviously, the first thing we've got to do is stick these somewhere where they won't blow off in the wind or get damaged by anything, and to do that, it needs some kind of support or clips. Now, often what you see is they're fixed to a roof, but they're not just rested on the roof. There's a framework underneath it holding them firmly, and I'm going to do exactly the same thing. But because I'm fitting mine to a flat roof, of course, what I need is some kind of cradle. And to make my cradle, I've got myself some steel. This bit of angle iron, which is 30 by 30, bit of flat bar 30 by 4 millimeters, and a bit of square tube 20 by 20. And I've got a simple design for a frame that I'm going to use. The next thing we need to do, cut some steel. Right, now we've finished the cutting. What we need to do now is a couple of jobs while it's still like this, because it's so much easier. This is going to be a foot, and a foot needs a couple of holes in it so we can bolt it to the roof. So we need to drill a couple of holes in the feet. And of course this bluey stuff is mill scale, so we need to use a flap sander grinder to get the mill scale off so it's ready to weld. And of course we have the flat bar, which needs a couple of holes in it as well, so we can clip the actual solar panel to the flat bar. Right, that's everything cut, machined and cleaned, ready so we can weld. So let's get the welder out. Right, now I've got 4 of these and 4 of these. I'm going to paint it with Hammerite. I'm going to use Hammerite because it's one coat and it's sitting in my garden. So all I've got to do now, get them painted. Okay, so I've got my sleds, brackets, supports, whatever you want to call them, right there. My solar panels are right there, and I've got to clamber onto that roof right there and fix them in place. So it's all pretty easy. All I've really got to do is bolt the panels in these holes here and then use these holes to fix it to the roof using roofing bolts. These roofing bolts are self-tappers and they come with a little seal on them, so they've got a rubber seal right on there, so you screw them in, they seal against the roof. At the back here, let me get this up, there we go. Yep. This is where those supports bolt in, right there, and they want this at the top so these can dangle down. Okay, that's them up, and you can just see them past the ladder, so clearly they're not that intrusive, which is exactly what I wanted. Now, it honestly doesn't matter much what you use to fix them up there. I made those sleds because I like making things out of steel, but it doesn't really matter. It only matters that you pay attention to your weather conditions. So I live in the south coast of Kent, north coast of Kent actually, and we rarely get high winds. I mean, we get them sometimes, but it's pretty rare, and we rarely get heavy snowfall. So the fixings I've used are really quite appropriate for the conditions I'm in. If you are susceptible to high winds or heavy snowfall, then you do need to think a bit more about how you fix them up. But to be honest, if the nail's big enough, you can fix anything. So the wiring of these things is actually pretty straightforward. I mean, I've got 4 panels at 12 volts each, so I could do a 12 volt system, a 24 volt system, a 48 volt system by wiring them in series and parallel. So if I line up plus minus, plus minus, plus minus, that's series. And if I do all of this with these, so I take the plus, connect it to this minus, take that plus, connect it to that minus, then what I'll get at the end of the chain is 48 volts. And equally, I can gather together all of the pluses and all of the minuses, connect them together, and what I get is a 12 volt system. Now, I want a 12 volt system. And for all those people who go, oh, no, you want a 48 volt system, no, I don't. I want 12 volts. You want 48 volts. I want 12 volts. Which means I'm going to connect these up in parallel. And that's basically gather everything together. So connect the plus to the plus to the plus to the plus and lead that down. Now, it's not that difficult, actually, because very often, and this one came with a kit with these beautiful little connectors, which is meant to join it up that way, whichever way I want it. And there's only one way they'll actually fit, and so I don't need to worry about them. Now, these connector sheaths are, of course, IP rated, but you don't actually need them. You could, if you wanted to, just chop them off, screw them, wire them together and put some sealant on them. But the connectors make it really convenient, and you can see they only go one way. So if I plug that into there and find exactly the same one from here and plug it into there, there we go, it's joined those up in parallel, and I can do the same thing with the other connector section, which is there and there. And now that's joined up in parallel. And of course what we've got is some pretty cables supplied by the company in the right colours, red and black. And they'll only go in one way, so what I end up with is this with the red and black coming down, and this is the bit that goes to the charge controller. I need to neaten it up, obviously, with a whole load of zip ties. So once we've poked it through the wall, of course, we're ready to attach our charge controllers. That hole there, well, I can weatherproof that again by squeezing in a bit of silicone. Okay, so on those wires, of course, I've got 4, because remember, I'm running a redundant system. I've basically got 2 systems that I'm going to bring together, and as I said, they're 12 volts. Now, I've been saying that I want a 12 volt system, and I want a 12 volt system for reasons, obviously. One of the reasons is because that's the voltage of automotive. Now, if you add recreational vehicles, cars, trucks, lorries, boats all together as automotive, it's an absolutely huge mass market, all running on 12 volts, and of course with a ton of ancillary equipment that will all run on 12 volts. It's because I've been bothered for quite a while about this. One of the things we do for transmission purposes is we transmit electricity around about 10,000 volts and step it down to 120 or 240, actually 230 volts, depending on where you are in the world. Then when it comes into the house, of course, we used to use that. But these days, what we then promptly do is step it down and convert it into DC to run So many things. I mean, your computer, your television, lots of things, your music centre, my 3D printers are all stepped down from the 240 volts to a DC voltage of some description or other, somewhere between 19 and 36 volts. Now, a lot of power has got to be lost in that because inverters tend to be around about 92% efficient or something like that. So we must be losing a lot of power. Why would we want to take a DC input, which is what the solar panels are, convert it into AC and then reconvert it into DC to run a whole load of equipment? That makes no sense to my mind. And I've always pondered what it would be like if you ran another system where you predominantly used DC and then at the point at which you're using it, you used an inverter only for those things that need an inverter. And of course, something like automotive, well, you can buy a 2 kilowatt pure sine wave inverter from your local store, Halfords in my case, for about £50. I mean, that's peanuts when it comes to that size of inverter. And as you go down in the size, so a 300 watt inverter is going to cost you about £20 or £30. They're really quite cheap at that level because the electronics are cheap and they're actually pure sine wave and really quite good. And then we only need them for when we need them. Because of course things like lighting, which is a predominant use, if you think lighting, entertainment and electronics is a predominant use that we put electricity to. We have additional stuff sometimes like heating, maybe the Hoover, the washing machine, the fridge, but a huge use of them is in DC form. So how would it be if we didn't bother with AC and didn't bother with an inverter and just run it on DC? That shed, you might have noticed, is a bit more luxurious than a shed. It's actually an outdoor workroom. I built it about 10 years ago and it's incredibly sturdy, which is why I can put solar cells on the roof and stand on it and jump up and down. Inside it, it's actually got its own distributed electrical system and it has its own lighting system. And it occurred to me that instead of mucking around with inverters, how about we just fed it straight in and we used that shed as a DC 12 volt voltage supply. When it comes out of the wall at 12 volts and we would need an AC supply, so for something like, one of the printers is AC, then use a cheap inverter at that point. Again, what we're looking at is redundant systems, because if we're only using an inverter at the point at which we need it, then if it goes, we don't lose everything. Now, of course, we do our 240, 120 volts to DC as a legacy. This is what we've used, and so a lot of equipment has been produced in order to use the supply that we've got in country. But going for the 12 volts automotive means there's also an awful lot of 12 volt equipment out there. And if we all did it and there was a sufficient market, of course, manufacturers would make it with the inverter, in inverted commas, inside the actual product, because an awful lot of products don't need inverters. I mean, sure, if we're going to do 12 volts, you might need a DC to DC converter, but that's not going to be very much electronics in order to do that, and I'm quite capable and happy to do that in certain circumstances, and it would be like a power brick. Just like that. But instead of being 240, it would be DC, whatever, 12 volts to DC out, whatever I needed. So we're already used to that idea with these things that you find on every single laptop. So I want to consider that as an idea, and I want to think a bit about that. Now, I've got the batteries, obviously, but I don't have the battery connectors. So what I'm currently doing is waiting for those to arrive before we install the batteries. So we've installed the solar panels. The solar controller, of which I've got two, are a piece of cake. There's just the little connections here and here that you connect in. The batteries are obviously going to connect those in parallel, and parallel means plus, 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 minus, 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 gathered together, instead of series, which is plus, minus, plus, minus. So we're going to connect them in parallel to run our system, or be the batteries for our system. And the big question is, do I feed that straight into the distribution board, which is in that shed, and use 12 volts at the point where I actually want to use it, and then get little inverters or DC to DC buck converters if the piece of equipment that I want to plug into my 12-volt supply needs it. Now, another reason we use high voltage like that, of course, is because of voltage drop over distance. But that shed, I mean, we're talking about 3 foot of travel. Voltage drop is not going to be an issue in a particular setup like that. Given that inverters waste about 8%, then that's quite an improvement in the system. Now, as I said, this has bothered me for a while, and I haven't done anything about it because it's my house. But now I've put the solar in the shed, it's something I can experiment with and see whether it's doable and if it is actually more of a pain than not. So the battery, I would argue, is one of the most controversial things in solar systems, with people being, well, almost evangelical about their choice in battery. But it basically splits down to one of 3 choices. There's lead, there's lithium, what I'm going to call exotic type of batteries. Now, lead batteries also split down into different types. The cheapest and simplest is going to be the flooded lead acid battery, or the FLA. It's the old kind of lead acid battery with nothing done to it but a load of acid chucked in there. They're not very powerful. They don't store a lot of energy. The energy density of them isn't particularly good, and they don't last a very long time. On the plus side of it, they're really very cheap. They're probably one of the cheapest options. Now I'm going to go with that. And I'm going to go with that because I have 4 of these sitting in my garage doing nothing. That's the only reason that I'm going to go with it, because there are lots of other choices. There's something called gelled lead acid batteries, and then there's absorbent glass batteries, and there's batteries in combination with carbon plates. And they gradually get better and better in terms of their longevity and in terms of their energy density that they can store, but they remain the cheapest option. There is one issue with flooded lead acid, and it is that it's basically electrolysis. And it's electrolysis of a water solution, so it splits the water. And it will split a little bit of water into hydrogen and oxygen. And of course, if you have massive amounts of them, that hydrogen can be a bit of a problem. The FLAs also have a little hole in the battery to let that hydrogen out. Later on, they came up with the anodes and cathodes that would recombine the hydrogen, and so you got sealed lead acids where that wasn't a problem because the hydrogen was recombined. But if you use this basic type, they are giving off a little bit of hydrogen, and if you don't remove this little plug in the hole, you will blow the battery out like a football. And if you have a lot of them, you need to make sure that the space is ventilated. With 1 or 2, it probably doesn't matter much, but with loads of them, you're going to get a build-up of hydrogen. And in the early days of lead acid storage, they made sure that it was ventilated. Now I'm going to put these in an outside cupboard because there's 4 of them, and I want to make sure that that isn't going to happen. So they're going to go into an outside cupboard. But like I say, later batteries that that are sealed don't have that problem because there's a recombination in the battery itself. AGM is well known for its longevity, but even so, we're only talking about a few hundred charge and discharge cycles when it comes to something lead acid. The biggest bonus is they're absolutely everywhere and they're dirt cheap, and you can buy something called deep cycle batteries where they can go up and down and last for absolutely ages. So they've got their quirks about them, they've got varieties about them, and if it's a choice you want to make like me because they're there, then nothing wrong with that, go right for it. You'll just have to recognise that there are also limitations that you have to pay attention to. But that's true of every type of battery. Every type of battery has limitations that you have to pay attention to. The current best battery, I absolutely hate that word, but it's the current battery that is in favour is of course lithium ion. And lithium has itself a whole bunch of flavours. There's one called lithium titanium dioxide where the charge cycle, it runs into the tens of thousands. It will last tens of thousands of charges and discharges. But again, the energy density is less than other forms of lithium and the overall voltage is lower than other forms of lithium, but it does come with the added advantage of lasting a very long time. Other kinds, the popular kind, lithium iron phosphate, again, it has discharge and charge cycles in the region of hundreds of cycles instead of tens of thousands of cycles. It's a bit more expensive, it's more energy dense, but it is an alternative. And of course, there are other forms of lithium that get gradually better and better in their energy density, the amount of energy they can store, but they also go in price. And of course they have a nasty habit, as people have seen, of bursting into flames that you can't put out. So there's a whole range of batteries available with various pluses and minuses about them, and at the end of the day you're going to make a choice, and the choice really is going to be what you want and what suits your budget, what you have lying around and what you want to do with your system. You can explore different kinds of batteries and weigh up their pros and cons for you, for your application. For me, there's never a best, there's one that will actually suit you. Now, another reason I'm going for these is because I want the adaptability of the system. I want to be able to change the system over time as I learn, because all that you do and everything you do is always a learning process. So I've gone for a system that I can adapt and change relatively easily without too much interference from one part and another, as I change my ideas, as I learn different things, as I experiment with different things. Because I did talk about the exotic kind of battery. An exotic battery can range from something that you can buy, like for instance nickel iron, which I know a lot of people actually like, and there's still factories that make these. I believe there are 2 in China still making nickel iron batteries. They're a very old battery and they supposedly have much longer life cycles. They're supposed to be much cheaper. But nickel iron is an interesting, already made exotic battery that you may want to turn to. And of course, for people who followed the channels for years, you know that I'm a battery chemist. So I'm interested in batteries that can be made at home. For instance, the zinc bromide gravity battery. Those kind of batteries I'd like to experiment with and see how it would fit in my small solar system. There are equally other things that I'm kind of keen about, and that is putting batteries and supercapacitors together, and how would that affect the charge, discharge and life cycle? Because research has shown that simple lead acid, its life can be extended unbelievably by the addition of a supercapacitor bank to act like a kind of sponge between the battery load and the battery supply. It's again something I want to be looking at. So adaptability is a big point in my system, and it might not be the point in your system. You're going to make those choices as you look at the various alternatives that are available to you and choose the one that's best for you. But all that aside, the batteries all connect up in the same way. And again, you have a choice, and again, you can bet your bottom dollar people will tell you that one way is better than another, and swear by it and give you hundreds of reasons, because thou shalt have only one battery and no other battery will go before me. And they'll tell you all of this stuff, but you're the one that needs to find it out and make your choice. But you can either connect them in parallel or series. Series is dead simple. It's just where you connect the plus and the minus together, and as you connect them together, the voltage goes up but the amps remains the same. And you see that in lots of applications like your radio, where you're just chucking a load of D cells in line with the bottom touching the top. That's in series. In parallel is where all the pluses are connected to one bar, the bus bar, and all the negatives are connected to another bar, a bus bar, and then the voltage remains the same, but the amps go up. So it just depends again what you want to do. I've chosen a 12-volt system for reasons I've explained, so I'm going to connect my batteries up in parallel to maintain 12 volts, but increase the amount of amps that I can store. Now that brings with it some kinds of problems, because DC voltage does suffer from something called voltage drop. If you run a cable 10 meters, the voltage at the beginning will be about a half a volt difference at the end. The voltage drops because of the resistance in the cable. When you're putting in a DC system, you have to pay attention to voltage drop. So my system is from my shed roof to inside of my shed. It's about 2 meters, so it's not an issue for me. If you're running at 100 meters, you might want to think again about something like 12 volts. You might want 2448, or you might even want more. One of the big advantages of things like 12 volts, of course, is it's a readily available market. One of the big advantages of keeping something below 48 volts is you don't need an electrician's certificate, because it's the low voltage regulations that kick in to anything below 50 volts. So again, things you need to consider when putting your batteries together. But the practical aspects of putting batteries together, that is, sticking them outside or in a protected container in case of a fire, linking them up in parallel or series, are always going to be the same. So once we've decided on our batteries, the mechanics of doing it are pretty much the same. So of course, if you're going to connect some batteries, you need some wire. And the question is, what kind of wire do you need? Because this is a 40 amp hour battery with 330 amps that it can deliver. So what am I going to attach it with? Well, this thing, it's not a demon. It won't reach out and grab you and deliver all its amps that it possibly can. It's going to deliver the amps that you need of it. And that's a key point here. It's what you actually draw, and that's dictated by the circuit that you attach to it. So in here we've got these lights at 12 watts. I'm planning on putting a 60 watt machine in there, so we're talking about 72 watts, maybe some more lights, say about another 8 watts, 80 watt, so we've got about 80 watts in total. Let's add a bit onto that and call it 120 watts. So I'm expecting to draw about 120 watts at 12 volts, which means that's going to be about 10 amps. So my draw is going to be about 10 amps. Now on the input side of course, I've got 2 solar panels, 120 watts each. They're delivering at 12 volts, more or less. So we've got about 24 amps coming in and about 12 amps going out, more or less. That's going to be the kind of maximum sort of figures. That means we need something that's going to be able to cope with a 20 amp load. Now, if we want to ensure that 20 amp load, of course, we put a fuse in there of 20 amps, but the wire has to be able to cope with it. And that turns out to be about 4mm CSA, cross-sectional area. As long as the wire is a minimum of around that, we've got a huge safety margin and we're not going to burn our wire. And even if it is, we stick a fuse in there to protect absolutely everything. Now, I've got these lying around. These are jumper cables, and the reason I'm using them is because they're lying around. And actually, they've got a 10mm cross-sectional area, 10mm squared cross-sectional area, and that's absolutely huge. You're talking about a cable that can handle 80 or 100 amps or something like that, and I want about 10 or 20 out of it. So yes, it's completely overkill, but as it happens, I had this lying around, so that's what I'm going to use because it's not costing me any extra. It's been in my garage for ages and I got about 6 meters of it. Brilliant. Of course, I can't just stick this on here. What I need to do is get some connectors, and what I need is some appropriate lugs on there, because with electrics, it's like anything. You take your time with it and do it patiently, you'll do a good job and it'll be perfectly safe. If you try to put a Jubilee clip round there and stuff that in and tighten it up, it'll work, but there's a question about how secure that's going to be and how long that's going to work. So we grab some lugs, we grab some wire of the appropriate size. These are actually standard sizes. This is an SC35-8, sorry. That tells you the hole size there and the size of wire that will go in there. So I trim off my wire, pop it into there, and then I've got a lug clamp, and I just squeeze it in that clamp. And when we've done that, we clean it up with maybe some heat shrink or some electrician's tape to tidy up these sides here so that it's nice and protected and looks pretty, and we've got no stray cables and nothing that can possibly touch. That's all the cables we need. So now we've terminated our cables, we need to attach them to here, and for that I've got these battery connectors. These particular ones I thought were kind of cute. They've got a couple of bolts at 6 and one at 8, so we can connect to there and use that as the lead out. We can connect to there to use that to connect either serial or parallel. Obviously there's one red and one green, or black. The red goes on there, that goes on there, and they're only the right size. This is 19mm, this is 17mm on this particular battery, just to check the size of your terminals. Then we tighten those up and do that to all 4 batteries. Okay, so here they are set up in the battery box, and so we've got the negative running to the negative, and running from the negative straight the way through, and that will go to the charge controller, and again positive to the positive, and you'll notice I've left the positive off for the moment, but that positive will then connect there, and go to the charge controller, and that's what we mean by being in parallel. And of course the bottom is exactly the same because it goes to its own charge controller. Now we drilled a load of holes in here. There's one in there, there's one in there. Those holes need filling with silicone. Not so much to keep the weather out, it will help keep the weather out, but when you've got a moving structure or a steel structure, you need some buffer in there to stop the structure sawing through the cables, and putting a whole load of silicone around that will do exactly that job. And there's my battery cables fixed to the wall and passing into the shed. Now these aren't rated for exterior use, so I've just put them to the wall for the moment. What it really needs doing is a bit of containment, or a box putting over that to protect it, because of course I'm hanging spades here, so we don't want that to get damaged. That's so you can see it. Containment needs to go around it. So there's my battery cables coming through the wall, and there are my solar panels coming through the wall. So obviously what I need to do now is put the electronics in. So when I say the electronics, of course, what I mean really is the charge controller. But to be honest, there's going to be more to it than that. I mean, one thing, I'm using redundant systems and I want to be able to experiment with it. So anyway, we're here in the studio and we've got our cables coming through the wall from the solar system that we're putting in. And of course, what we need to do now is add the switch gear and the control electronics so we can actually get what comes in and our batteries to put something out so we can light lights and run sockets, that kind of thing. Now to do that, I tend to be a little bit anal about some things, and arranging electronics is one of those things that I do tend to be a little bit conservative about. So what we're going to do, in order to keep it organised and so that I can experiment with it easily later, is we're going to put it on a board. I mean, I could just screw it to the wall, but I'm actually going to put it onto this board here. In order to make that board stand off, I've got some door stops. So these are the old-fashioned door stops that are 1 inch high, or 24 millimeters, and 30 millimeters across. And when I put them on the back of here, they're actually going to make really good standoffs. So we need to put this onto the wall where it covers over these cables and create holes in this so the cables can come through the board. So let's do that. You might have noticed that I did tag these before I started doing that. I put a bit of tape around them so I could tell which one was which, because of course I've split the board into System A and System B. System A is going to be all our DC stuff and System B is going to be all our AC stuff. And as I said, experimentation, but I tagged them. You have to remember to tag stuff or you'll never remember which way around it is without doing an awful lot of work to try and find it. So just put a couple of tags on the ends of your wire. Okay, so we've got everything sorted out. Now then, what we need to do is basically isolate everything. So I've got these, which is a couple of miniature circuit breakers, and they go to the solar cells. So the solar cells have a DC MCB. This particular one is 6 kiloamps at 1000 volts. So very much overkill, hey, for what we want. But that's going to go on there, and the solar panels will come into here, and then they'll come out of here, and then they'll go into the solar charge controller. So there'll be one there for System A and one there for System B. So let's put those in. Right, now we've got our solar panel isolators on, we need a battery isolator, and that's what this will do. This is rated at anywhere between 12 and 48 volts and about 400 amps. So it's going to do the job fine, and we're isolating the positive. So we need to put a lug on here, then that will bolt on there like that, and our out will come from here with another lug, and we just screw it to the board, and again 2 of them to isolate the batteries. So that's the switch gear finished. Now we can isolate the solar panels, we can isolate the battery. All we've really got to do is terminate this, the negative, and you might notice there's a bolt right there. Again, there's loads of ways you can do this. We could put in a negative bus bar if we wanted, but that bolt will just perform the same function. We pop a lug on there, attach the negative to that. Then we can attach all of the negatives to here that we need to attach, and of course we have our negative return. When I've done that, what I'll do is I'll trim this off, and when I trim that off I'll 3D print a cap that goes on it so it's nicely capped off. But we need to terminate the negative, and we need to give negative a way to connect to other things. A bolt or bus bar works just as well. So now let's put a lug on this and bolt it down. Right, and there they are in place. Now then, we've finished with that switch gear, we're ready for the control gear, which is basically this. As I said, this is a PWM solar controller. We discussed that much earlier in a much earlier video. An MPPT controller will be exactly the same placement. All we do is screw it to the board, and then of course we've got a list of connections here, and it tells you what they are. There's the load, there's the solar panels, and there's batteries, and there's a little symbol above the plus and the minus. So we screw it on there like that, and then we just connect up these wires. Okay, and that's it all fixed down. Now it's really nothing more than crimping on these spade terminals, sliding them in there, and tightening down the screwdrivers. It's ready to go. Of course, we've got System A and System B because we're going to do one at DC and one at AC. With DC, there's actually not much more, in fact, nothing really to do with it. There's a little output here called load, and you can connect straight to that if you want, but it's not tremendously advisable. I mean, this would be, I guess, fine for one application, but of course we've got lights outside, lights inside, probably going to put some phone chargers. There's a LED driven cure station that's DC that I want to run off of it. So there's a few circuits that I want to be able to run from System A, and I'm not quite sure what else to do with it. So I've got this. This is a fuse board. It's a fuse board meant for caravans, buses, cars, boats. So it's up to 48 volts. There are 12 circuits. The little LEDs light up to tell you it's working. It's got a plus and a minus. That goes slap bang there. Then from our load here, we take the plus, load here, we take the minus, and we take the minus to here and the plus to there. Then we've got a distribution board that we can distribute our DC circuits from, where that is the negative and the positive goes in here, and of course your fuse goes in there. So for the DC, we need to fit that. Now, for the AC, what we need is an inverter. So here we've got the straightforward stuff. Very often you find the controllers and the inverters in one box, which is awesome until one bit goes wrong, of course, when you have to pay to have the whole thing refurbished or throw it away and buy a new one. All we've done is split the controller from the inverter, and I'm using 2 bits of equipment to do the job, and this is a 150 watt inverter. The reason it's a 150 watt inverter is that I don't really intend on doing much on AC here anyway, with a maximum load of about 60 watts for the 3D printer. So you normally find your inverter sitting right there. So we've got for the DC a fuse block, for the AC a straightforward inverter that we can just plug into. But I have had a little bit of a change of heart, and we'll talk about that in a minute. Let's get the fuse board on first. Okay, so there is the fuse board on, and here it's going to the load from the actual controller to the negative, and then the positive to the positive load on the controller. There's one circuit, which is my outside lights, and we did that in a previous video, how I used a buck boost converter to change the 12 volts to the volts needed, but it joins on the neutral here, and then of course it's on that side of the live with a fuse in there. So it's all fused up and ready to go. Snap the cover on. We want to add circuits. We've got up to 12 circuits, and each circuit can max out at 30 amps. So a reasonable size fuse board. Now, although my system is built a certain way for I want it, the logic here is always the same. Your solar panels come in via an isolator. Your battery comes in via an isolator. You'll have some kind of charge controller and some kind maybe of inverter, and then some kind of distribution board. This distribution board, in my case it's fuses, but it's distributing the power from here around where you want to use it. That is the fundamental of any solar setup, and in fact a wind setup looks very similar as well. Now, as I say, I've had a change of heart about this bit, and we're going to talk about that in a second, but having 2 identical systems like this means that I can actually leave one alone and change the other, and of course compare the 2. So that's a big thing for me. It may not be for you, in which case yours is going to look just like that. So here is my change of heart. The only AC bit of equipment I want to use out here at the moment is this thing here. It's the Halot X1 that was sent to me, and it's 60 watts. This cost me £25, and I can think of it like a reverse power brick, if you like. And with a lot of things that are DC, for example, this one here, which is the curing station, it comes with this, and that changes AC to DC. This changes DC to AC. So I was thinking, well, why not just keep the whole thing DC? And at the point that I want to use it, use something like this, which is pretty much cheap actually, and just stick it there and then have the whole thing DC. So that's what I'm probably going to do. And of course, I've ordered a new fuse board to do exactly that and keep those two systems actually identical. And then I can test one against the other. Right, that's it, so ready to go. Now, of course, I've left it exposed so you can see it, but it does need a protective cover around it, like some kind of cabinet maybe. But batteries on first, and my surge power controller starts, and then we flip on the solar panels, and it'll start charging the battery, and the lights that we attached are going to be able to be turned on. Originally, they used this thing. It converts the AC voltage at 230 volts into a DC output of 30 volts. Equally, in my shed, I've got a 12 volt supply. And now this is a really common situation where you have one supply but another load that differ in the terms of voltage. You're going to find it in things like running computers, running your TV, charging your phone, that sort of stuff, where your supply doesn't match the voltage requirement, and that might seem like a problem, but the solution is right here. Well, this tiny thing is a DC to DC buck boost converter, and it is the XL6009. It's taken over from the LM2577 as being more efficient, and as you can see, it's tiny. Now, I bought 8 of these, and this cost me £1.50. What it'll do is it'll take anywhere between 3 and 30 volts in and change it to 5 to 35 volts out, and this little device will handle 4 amps. Now, that's more than enough for the fairy lights in my garden, and to use it, well, it's that way. It says in there and out there. So the 12 volts go in there, and when I set it, the 30 volts will come out of there. And the way I set it is by twiddling that little screw up and down. So I get a 12 volt supply and stick it on there, and a multimeter and stick it on the out, and I twiddle that screw until the multimeter reads the voltage I want. As you can see, it's currently reading about 22 volts. If we turn it anti-clockwise, then the voltage goes up. Clockwise, the voltage goes down, and we just twiddle that until we get the voltage output we want. So to fit this, of course, we have to bring the wire into the building. So the lights are on ahead, it's clipped to the top there, and it comes down here and through that hole into the other side of the building. But you might notice this. This is actually called a drip loop, because in a rainy country like the UK, if we put it straight into there, the rain would follow down the wire and go straight into there. What it does is follow down the wire and collects here and drips off. It might seem like a little thing, but actually that's essential when it comes to putting wires in a building in a country like the UK. So to fit this, I knocked up a simple project box on the 3D printer, and that will basically go in there. Now, I want to be able to turn these on when I'm at the house. I don't want to stumble up the garden in the dark and turn them on. So I got this, which is a remote switch. On this remote switch, just like a normal switch really, there's the input, so that will go to our power source. This feeds in through there and connects to the inside of this board there, and the outside of the board connects to the lights, and that will feed out through there. So we need to solder that onto that. There they are on the wall. Now all we need to do is strip the lights wire back and solder it in place here on the out, then a bit of hot glue to make sure it doesn't touch the screws, and we can put the cap on, and that's it, finished. This, as I say, goes to our power supply. So let's strip that back and get it hot glued in place. Okay, that's it, caps on, and we're finished. Now we need to connect this to its power supply and pair this to the key. If we were doing this as just a normal switch, then the chances are that little buck boost converter would fit in the switch and you wouldn't even notice it. But let's get this paired. And when you've done that, what you get is this. That's pretty cool, isn't it? So, what we've done is take one of these, which is a DC to DC buck boost converter, take our 12 volt supply, twiddle this little screw on here and get our 34 volts that we need to run our application. And of course, you can do that for any DC to DC using one of these. This particular one is limited at 4 amps and it's £1.50. You can get them much more powerful than that. I mean, this is about 120 watts. You can get them to anything. Of course, they do go up in price the more you get power handling capabilities. So something like this application needs next to nothing. Now, one of the good things about automotive RVs, boats, of course, is the 12 volt market has a lot of stuff that's just sold off the shelf. But sometimes it can be a bit of a premium, which I think is a bit mad, because it's absolutely no trouble. I mean, you saw how easy it was. It really was as simple as twiddling that little brass screw to take a £1.50 piece of equipment to do this, and it would be the same. I mean, this would run a computer, run most televisions. It's really quite simple to do and relatively trivial, in fact. Now, at 12 volts, there's pretty much nothing to be afraid of. I mean, you have to be standing in a suit of armour with chairmail on or standing in a pool of salty water to start worrying about something like 12 volts. That's why the low voltage regs finish at 50. It doesn't matter pretty much at 12 volts what you're going to do, unless of course you short it across the terminals with a spanner, in which case you'll melt the spanner. But it's not going to do anything to you. It's really no trouble at all, which is why I like that idea. And you do have to pay an extra £1.50, but I think it's a hell of a lot cheaper than buying an inverter and then using the power brick to take that inverted AC current back down to DC with all its concurrent costs associated with it and lack of efficiency. It's one of the things that really attracts me to it. So putting in a little board like that is really the plan for anything that is, for me, anything that is DC to DC. So I hope you enjoyed the video. I hope it really showed you how easy it actually was, and in fact how practical it is to be able to do something like this yourself. It really is quite easy. So I hope you enjoyed the video. Thank you very much for watching, and please do remember to like and subscribe.